This section is titled Double Integrals. Any idea why we might have the word double there?
Because there's two of them.
Okay, yes, there's two of them, but why would there be two of them? Because we're working with two variables. That's exactly right. So we're going to be taking a look at doing integration now with two variables, just like we were doing derivatives, or in this case it was partial derivatives with two variables. So let's start by talking a little bit about how that worked. Do you remember way back in Calc 1, when you very first encountered integration, how in the world was this all sort of described or defined? I mean, what in the world was the purpose of finding these things called integrals? It was area under curves. Do you remember that? Area under curves, good. But you didn't do it first by finding integrals. How did you do it?
Squares.
Rectangles. Yeah, and there, you may have done something with trapezoids or different things like that too. The general sort of idea is rectangles. So you started with something that looked some kind of a curve, and you created the space underneath it, and you split it up into a certain number of intervals. A lot of times it's 4. When we first described, we split it up into 4 intervals equal. And then you have some options. You're finding the areas of these rectangles, so what do you do to find area?
Base times height.
Base times height. Now, the bases are all the same, right? Because we've equally split up the interval, but the heights are different, at least potentially so. They're based on the function. And so how did you decide what height to use? Because the function, in most cases, was not actually a horizontal line that actually really created a rectangle. Sometimes it was an average.
Just, take the base times all of the right side together.
That's true. You do. You do that eventually, yeah. Before that, though, how do you get the heights is what I was asking about, actually. There's 3 basic ways that we did it.
So like the distance.
Nope. So let me kind of draw a sketch that might help sort of discuss the idea here. So if you have this kind of an image and you were finding the area of this rectangle, here's your base. What did you do for the height?
Start at the left, the right, and the middle.
Those were the 3 places you normally started, either the left-hand side, the right-hand side, or the middle. Okay, so let's talk in general about what happens now in 3 dimensions. Because in 3 dimensions, this isn't quite so simple. There's not a left, right, and middle. What does it look like to be under a curve? Well, right now, instead of being under a curve, we're under some 3-dimensional surface. Okay, so imagine a canopy or something like that. Okay, you've got this sort of a 3-dimensional shape, and it's above the XY plane, so it's above the floor. What we're going to do is we're going to find not the area, but the volume underneath that 3-dimensional or underneath that canopy, that surface space. Okay, so we're going to be finding volume. So the first thing we're going to do is that we're going to do it again with the equivalent of that idea of rectangles, and it's called Riemann sums. That's the official name that you heard for it back then. And we're going to be doing it then, instead of with rectangles, what would be the 3-dimensional equivalent? Prisms. We're going to do it with rectangular prisms. Okay. Now, it's pretty simple to talk about the base of the prism. It's just going to have a specific length and width, kind of like the base of this interval. Whatever it was a set value, right? But the height of it is a little bit less convenient to discuss. And you can't really say left, right, and middle. You're going to have a little bit more description. All right. So that's kind of where we're headed as we start this discussion today, and we'll develop it a little bit more into that integration idea that we mentioned at the very beginning. So let's start first with definition 1.1. It says the following. For any function f defined on the interval this is the function definition, or I'm sorry, the Riemann sum definition you're used to. The interval AB, we said the definite integral of f on AB is the integral from a to b f of x dx. That's the notation. And what it is it's actually the summation. So leave just a little bit of space. I'm going to put something there in a minute. This is the summation of not just 4 rectangles, but, 1, from I equals 1 to n rectangles. As you said, you take the function value at some number, some value on the interval, and you multiply it by the width of the rectangle, which we designate as delta xi. Now for us, we're going to leave these delta xi's fixed, so it's just going to, we could represent it just as delta x because it's going to be a constant. But we do this as the limit of the size of our partition. If you remember that P stands for partitions, this is magnitude of the partition, goes to 0. So as these rectangles get infinitely narrow, right? That's what this is saying. As our rectangles get infinitely narrow, sometimes you'll see this defined as the number of rectangles get infinitely large, because that's the equivalent description of that. A couple of things just to be clear out. This is provided the limit exists. And is the same for all choices of evaluation points C sub I on the interval x sub I minus 1 to x sub I, for I equals 1 all the way up to n. So this condition is not possible if we really have I mean, at least as a general statement, is if we have a finite number of rectangles, but our rectangles are becoming infinitely many. So that evaluation point will happen to be the same because the intervals go to 0. The size of the intervals go to 0. In this case, we say that f is integrable. We do. Integrable on AB. Okay, so this is the version this textbook uses of this definition of Riemann sums, of finding definite integrals with Riemann sums specifically. So what we're going to do is we're going to take this definition and broaden our horizons to include this, like we described, as a function of two variables, two input variables, not just one input variable. Okay, so f of x, y instead of just f of x. So that's our next definition that we're going to look like, and you'll see a lot of parallels in definition 1.2 to definition 1.1. So for any function f defined on the rectangle, and we will generalize this word rectangle in a moment. I know that sounded a little bit weird to even say that way, but we're not always going to be working on a rectangle. We are for the moment. The rectangle R, which is x, all the points x, y, such that x is between A and B, and y is between C and D. We define the double integral of f over R by, so just like you had mentioned earlier, we're going to have the double integral symbol, so two integral symbols. We're going to put the interval R right here, and we'll talk later on how we can sort of develop that a little further, of our function f of x, y over an area. So this is dA, and we'll develop that a little further later as well. Again, this is a limit as a partition goes to 0. So we're getting infinitely many of these rectangular prisms of the summation from I equal 1 to n of a two input function u sub I v sub I times delta a sub I. Again, with some conditions, provided the limit exists and is the same for all choices or any choices of evaluation points u sub I v sub I in the intervals R sub I region for I equal 1 to n. When this happens, we say f is integrable over R. It's a very similar definition to the other one, right? Instead of having an interval, we have a rectangular region.
I have a question.
Yes?
I missed it on your double integral. Why do you have the R?
That's the region over which it's integrable. So we defined this R up here to be letting the x values go between a and b and the y values go between c and d. We're actually going to write this a little bit later where where we, instead of writing the R down below, we're going to actually put the A and the B and the C and the D in.
Okay.
So we will do that. And we will change the DA at the end as well to say something different to reflect that. So the notations are very generalized at this point and they'll become more specific later. Okay, I think we need an example to see how this works, don't you think? So let's do that. All right, we're going to compute the Riemann sums for the given function and region with a partition of n rectangles. And I'll explain what I mean by why that says rectangles instead of, say, rectangular prisms. Rectangles divided as indicated. So our first function, f of xy, is x plus 2y squared. And our rectangular region is that x is going to go between 0 and 2, and y is going to go between -1 and 1. And I'm going to write what they have written down, although I think they probably could have left this off and you could figure out that this would be the most reasonable choice anyway. We're going to, well, this next part's not, okay, I got ahead of myself. First, you need this part. We're going to evaluate at the center of each rectangle. So that's equivalent to saying we're using, quote-unquote, a midpoint rule, right? In 2 dimensions, this would be like a midpoint rule. The part that I was referring to, I'm sorry, in a moment here, is that the first thing we're going to do this for is n equal to 4 rectangles. And the part that I feel like is a little bit of overkill is that they tell you that you're going to divide at x equal 1 and y equals 0. So let me show you why I think that. So the first thing we're going to do is that we're just going to draw a 2-dimensional shape of this rectangular region. So my rectangular region is supposed to go from x equals 0, which is the y-axis, out to x equals to 2, right? And it's supposed to go from y equals -1 up to y equal 1. So my region is right here. That's the rectangular region they're referring to. So this part that I put sort of in these braces right here that says divided x equal 1 and y equals 0, well, that makes sense. That divides it into 4 equal little rectangles. You're just cutting them in half. Are you with me? That's all you're doing, is you're cutting this graph in half. So one of them's already there. In fact, this one's already, oops, let me use a different color. This line's already here. That's y equals 0. And they're saying split it like this as well. That's x equal 1. And I've split this into 4 little rectangles, and they're all equal area. And just for the sake of we're going to need it later anyway, what is the area of one of these rectangles? The individual area. It is 1. It's got a width of 1, it's got a length of, or height of 1, however you want to think of it. So we've got each of those individual areas has area 1. Okay? All right, so here's what we're going to do. We are supposed to be finding the summation from I equal 1 to 4 of our function evaluated at midpoints, which we'll get there in a minute, of u sub I, v sub I, over delta a sub I. So you mentioned, Caleb, earlier that what this is, what we really do in practice, is we add up all the heights, and then we multiply that by, previously, by the width. Well, in this case, by the area, because all the areas are the same. So we are, in fact, going to do that here as well. We're going to multiply by our area, and we're going to have all of our heights. Now, our heights, I'm going to write in that we're going to measure each of them in the right location. So we're supposed to be measuring our heights in the middle of these rectangles. So that is to say, we need the ordered pair at each one of these midpoints. So like we need to know what this ordered pair is, this ordered pair, this ordered pair, and this ordered pair. And I think you guys can tell me them. So tell me one of them.
I'm still struggling. How's the area 1 and one of, is it in one of the little squares? Or?
Yes, for each of the individual squares, the area is 1. So like the area here is 1, the area here is 1, the area here is 1, and the area here is 1.
Isn't the height 1/2?
The height goes from y equal -1 to y equals 0, and then 0 up to 1. Yeah. So this is 1, and this is 1.
And 4's on top because we have 4 squares.
Yes, we have four squares. There are squares in this shape, but yeah, we have 4 rectangular regions we're working with, exactly. So we're making 4 summations. We're going to find 4 heights, and we're going to multiply those 4 heights sum by the area of the base. Okay. All right, those 4 dots in the middle, can somebody tell me what the top left corner location of that point is? Yeah, it's 1/2, 1/2. Does everybody see that okay? Now's the time to say something you don't, because we're going to keep going to the other 3. Okay, what about next to it? What about the top right corner? 3 halves.
That's still
1/2, right. What about the bottom left corner? Yeah, 1/2 and then -1/2, good. And then the bottom right corner? 3 halves, -1/2. So you told me that our areas are 1, and we talked about that a little bit. Now we need to find what is our function value at these 4 specific locations. How do we do that? Plug them in where, Jordan? Right, the very original equation that we were given. So this would be one of those activities, depending on how complicated the function is, that you might want to use the store feature in your calculator. These aren't especially difficult to do by hand because the function is not especially long. But we do need to have 4 function values. So in an effort to save some time, why don't we have 4 of you find each of the individual ones? So Caleb, can you find the first one for us? Taylor, can you find the second one? Tally, you've got your calculator. Can you find the third one? And Nathan, find the fourth one. Okay, so you're going to plug in that number, 1/2, 1/2, or 3/2, 1/2, into the equation x plus 2y squared. All right, did you get one, Caleb? Were you telling me your answer?
I think it's 1.
Okay, so you have 1. Okay, I agree. That's what I have too. Taylor, did you get your second one? You had 2 on yours. Tally, did I give you the third one?
Yeah.
It's okay. Good. And Nathan? All right. So add them together, quote unquote, multiply by 1, and what do you get? 6. So the approximate volume underneath this surface back down to the xy plane is roughly 6. That's our approximation. All right, so just for fun, we're going to go one step further. And how many rectangles do you think we might do next?
74.
74. Man, you are
You
ambitious.
can do a 74.
I'm with Taylor. I think let's do 8. And they do this another awkwardness, I feel like, a little bit, but they tell us how to divide it. We're going to divide at x equals 1, y equals negative 0.5, y equals 0, and y equals 0.5. It's a little more necessary on this one, as you'll see why in a moment. We don't actually get squares this time, I guess, is the kicker. So in terms of our region, let me draw a little bit bigger picture since we're going to divide it up into more stuff. So here's my overall rectangle that I'm working with. It's not perfect, but it's okay. I'm supposed to divide it along x equal 1, and I'm supposed to divide it along y equal negative 1/2 and y equal positive 1/2. It looks worse when I divided it, didn't it? So I do actually have rectangles, legitimate rectangles, as in not squares this time. What's the area of each of those individual rectangles this time? It's 1/2. They still have a width of 1, right? But now they have a height of 1/2. All right, so we're going to find from I equal 1 to 8, because we're going to have 8 rectangles, f of u sub I v sub I times delta a sub I. So like we said, this is delta a is actually 1/2. So I need to know what in the world are my 8 evaluation points. And why am I choosing to put these in the middle of these rectangles? What was the reason for that? We are finding the midpoint, but why on this one are we using that particular method? It told us to. So it's going to tell you what method to use. So if this says use the upper left-hand corner, that's the numbers you would use. Okay, so it's going to tell you in the problems where to evaluate it at. All right, so top left-hand corner, what is the evaluation point there? All right, 1/4, yep. I think it's 1/2, right? 1/2. 3/4. So this is the point that I'm referencing right now. I'm just going to work from my top left, and then I'm going to go down and around, or zigzag down, okay? So that's 1/2, 3/4. What's the one right next to it, to the right? 3/2, 3/4. What's the one in the second row? 1/2, 1/4. And then right next to it, 3/2, 1/4. Okay, now we're actually underneath the x-axis. So the first box underneath the x-axis is negative, I'm sorry, 1/2. got my negative in the wrong spot. 1/2 and then
Negative.
-1/4. Okay, to the right of that is 3/2 -1/4. And then our bottom row on the left, 1/2 -3/4. And then finally 3/2 -3/4. And there are 8 points, and how many of you are there? There are 8 of you, so we're going to give each of you one of them. All right, so we're just going to go around. Brandon, you're going to do the first one. Nidra, you have the second one. You're going to evaluate. James, you've got the third one. Taylor, the fourth one. Tally, the fifth. Caleb, the sixth. Jordan, the seventh. And Nathan, the eighth. And you're going to expect to see some repeating values here. This is a somewhat symmetric graph anyway because of the y-squared part of it going on. So plug in the point that you were given into the equation. I don't have it on this screen, but my equation was f of xy equals x plus 2y squared. Let's do it in decimals because it's going to clean up really nicely at the end anyway. If the answer you get when you're working in decimals ends up being something that's a repeating or whatever, we want to turn it back into a fraction, just as a general rule of thumb. Otherwise, you can leave it as decimals or put it in fraction form. Brandon, do you have yours?
Yeah, 1.625.
Okay. So Brandon's 1.625. Nidra, did you get yours?
2.625.
Perfect. James?
0.625.
Taylor?
1.625.
1.625. Tally?
0.625.
Caleb?
Here, 0.87, but is that wrong?
That is wrong. Try that one again.
6 plus 2y squared.
Mm-hmm.
Oh, I know what is wrong. Okay.
Okay. I think everything has a 625 on the end, actually.
Yeah, that's why I was concerned.
Yeah.
1.65.
1.625. All right, great. Jordan? Nathan?
2.65.
All right, so add all of those decimals together, multiply by 0.5, and what do we get? Did you get a sum, Jordan? Not yet.
I didn't start yet.
That's okay. And we expect it to be close to 6 because that's the answer we got last time, right? So if your answer comes out something like 152, then we've got a problem. 6.5? Has anyone else gotten to the point of having a value?
That's what I got.
Perfect. That makes 3 of us. So 6.5 for our volume under this curve, our approximation using this method. Obviously, this is tedious, right? Yeah, this is a slow process. So this is sort of akin to when you do derivatives, doing limits to find derivatives instead of knowing the simple rules for doing it, right? And somewhere along the way, maybe you said it or you've heard people do it in the Success Center and they say, why do I have to do it the long way when I know the shortcut? And part of the answer to that is because then you appreciate the shortcut so much more, don't you? So let me take a look with you and talk about then using this idea, what we can do as a quote-unquote shortcut for doing this process. And it'll actually allow us to give values that are precise instead of being approximations. So this is theorem 1.1. It's called Fubinis Thm. And it says the following. Suppose that f is integrable over the rectangle. And we're going to have that same rectangle we set up before, R, which is the points x, y, such that A is less than or equal to x is less than or equal to B, and C is less than or equal to y is less than or equal to D. So those are our bounds for A and B, or I'm sorry, for x and y. Then we can write the double integral of f over the rectangle R as either of the following. Okay, so this was the notation from the last definition. Double integral over R of f of x, y dA. So we can either write the integral from A to B, the integral from C to D of f of x, y. Pay attention to what I'm going to do next. This says dy, and then it says dx. And this is equivalent to writing it the other way. We can go from C to D, and then A to B of f of x, y, but then we go dx, dy. Okay, so let's take a look at what's actually happening here in terms of the notation. This piece right here, whoops, it's not much better. This is a nesting function, right? It's inside of something else, like a composite function. So the reason that we have the y first in the first one is because the y corresponds to the limits of integration c and d. And then on the bottom, the reason we have the x is because the x is corresponding to the limits of integration a to b. Now, if we're doing this over a rectangular region, we can pick the order in which we do this. There's really nothing special as long as a, b, c, and d are all numerical values. Now, they're not always going to be numerical values. We'll get there in a minute. But for right now, we have flexibility and we can do them in either order. And that's what this theorem tells us. So we're going to actually find the volume of one of these. Find the volume beneath the surface and above the rectangular region. And our curve is defined as z equals 3x squared plus 2y. Our x value is going to go from 1 to 3. And our y value is going to go from 0 to 1. So we're going to set up two integrals, and you guys get to pick. What do you want to put first? Do you want to put the 1 and 3 first, or the 0 and 1 first? 0 and 1. Like this?
No, I thought you meant
The other way?
Yeah.
You want 0 and 1 here.
Yeah.
Okay? And then the 1 and 3 here. Okay? Our function 3x squared plus 2y is going to go inside here. And then because my 0 to 1 is the inside function right now, like the inside integral, do I put dx first or dy first? Dy. And then I put dx on the outside. So we're going to focus on this piece of this first. So we need to find, and you haven't actually done one of these yet. You haven't found an integral where you've actually got two variables. There's not a lot different from when we were doing differentiation, because you have to remember that since we're working with the variable y, what is x? It's a constant. Okay? So that 3x squared is a constant. It's just a number. So when I take the integral of 3xy, I can do it again, 3x squared, what do I get? 3x squared y. And then when I take the integral of 2y, I get y squared. And I need to evaluate this at the numbers 0 and 1, and then in a moment we will do the second piece of this, but for now I just need to have it written there. So I'm still working inside of what I'm sort of boxing in as my red rectangle. And Caleb, just in case anyone didn't catch why you did it, I know why you did it. Why did you choose to do 0 and 1 as the inside? And James, you echoed wanting that as well. Any idea why you would want to do that? Because the 0 is very nice. Why is 0 so nice? Yeah, I mean, things evaluate at 0, they just go away. So it's a wonderful feature. And evaluating at 1 is also very clean because things tend to go away in a different fashion, right, with evaluation by 1. All right, so we're putting 1 and 0 in for what variable? Y. All right, so if I put in the number 1 in for y, what do I get? 3x squared plus 1. What if I put the number 0 in? I get nothing. So this is the evaluation of the part in red. And now we're going to integrate from 1 to 3 with x as my variable. So what is the integral of 3x squared? X cubed. And then we've got the plus x. Very good. And we're going to evaluate this at 3 and 1. So evaluate at 3, I get 3 cubed, which is 27 plus my 3. And then if I subtract my evaluation at 1, so 1 cubed is 1 plus 1. So what is 27 plus 3 minus the 1 plus 1? 28 is correct. And you guys just did your first true double integral. Very well done. Okay? All right, so we're going to expand what we're doing now just a little bit more. This definition that we worked with, or it was a theorem actually that we worked with over here, defined this as being over a rectangular region. All right, the surface was on top of a rectangle. Well, the surface doesn't have to be on top of a rectangle. It could be on top of some other curve. So imagine instead of a rectangle being on top of a circle or something like that. So in the two-dimensional plane, on the floor, if you will, you've got some other kind of a curved space. And you're looking above that curved in space, in the third dimension up above. So that's where we're going to get our next definition. Definition 1.3. For any function f defined on a bounded region R, so this is not rectangular necessarily, any bounded region R, which is contained inside of the planar space, R2. We define the double integral of f over R by, so we've got that double integral notation of over R of f of x, y, delta A. This is my limit as my partition goes to 0 of the function from I equal 1 to n of f of ui, vi, delta ai. Provided the limit exists. And is the same for all choices of evaluation points ui, vi. Let me write that way. In Ri. For I equal 1 to n. In this case, we say that f is integrable over R. And for all practical purposes, the only thing different between this definition and definition 1.2 is what? R. It's the only difference. It's how they've defined R. We specifically defined R before to be a rectangular region. Now we're generally defining R to be any region in R2. Yep, Nathan?
Because I was 1 to 2 to n to what? I at the bottom, I was 1, 2, all the way to n to.
And then it says, in this case, we say?
Oh,
Yeah, in this case, we say that f is integrable over R.
okay.
So, you'll be very happy to know that we're not going to go through that process we did again with the rectangles. We're going to jump right to the theorem this time and use the theorem to do the operations instead, okay? So, our equivalent to the last theorem is theorem 1.3, and it says the following. Suppose that f is continuous on R defined by, so we are going to define R, but we're not going to define it as a rectangular region. We are going to define it as a set of points. That makes sense. One of our sets of points needs to have limits of integration that are constants. C and D is the one we're going to go with right here. And I'll show you another way of showing this. I can't remember if it's on this definition or theorem or another one. And we have h1 of y less than or equal to x less than or equal to h2 of y. For continuous functions h1 and h2. Where h1 of y is less than or equal to h2 of y. For all, you guys familiar with that notation, right? From Dr. Nichols, for all?
Yep.
For all y in CD, then the double integral over our region R of our function f of x, y, dA can be done by taking the integral from C to D, the integral from h1 of y to h2 of y, of f of x, y, dx, dy.
What's the
End of DA. Parentheses there or something.
Which one are we looking at?
In the end double integral at the end of, right after the DA.
Oh, I've got an extra line there. Sorry about that. You're right. I wanted an extra set of parentheses. It sounded like fun. I guess I skipped to Theorem 1.3. Theorem 1.2 looks the same, so they could have been done in any order. I'll do Theorem 1.2 next. Theorem 1.3 says that we could put the C and the D on the outside, and we could put functions of y inside, and then we could do an integral with respect to x first, and then an integral with respect to y second. All Theorem 1.2 does is it does it in reverse order. So you're going to feel very much like I'm writing the same thing, but go ahead and jot it down because it is important to realize that it can be done in either direction. Does everyone have this one written down so far? Okay, I'll wait. Okay. So let me jump back then and grab theorem 1.2. So it starts out the same way. It says to suppose that f is continuous. In fact, you know what? We're going to do it like this. Suppose that f is continuous on R, and it's defined by, the pieces I'm going to change are going to be inside of here. This is going to be defined differently. Okay, so what I'm going to define is I'm going to define that x is between a and b, and instead of the function instead of the function h, we're going to do a function g, 1 of x is less than or equal to y is less than or equal to g2 of x. I know this feels a little bit awkward. I promise when you see it in practice, it's not near so awkward. These are functions g1 and g2, where g1 of x is less than or equal to g2 of x for all x in AB. Then our region can go from A to B with dx on the end, g1 of x up to g2 of x with dy as our first integral. You have it, everyone? Fabulous. Okay, let's do an example so I can show you that it's not as near as odd looking as it sounded. All right, our directions are the same as what they were before. We're going to find the volume beneath the surface and above the region. It's not a rectangular region, but it is a region. So we're going to find the volume beneath the surface and above the region. And it's already set up for us as well, this particular one, and the ones that you're going to do like this will be as well in your homework. So this is an integral from 1 to 2. The second integral goes, or the inside integral goes from 0 to 2 over x. And we're going to do something that's not a polynomial this time, e to the xy dy dx. So if you'll notice, the primary difference from what we did before is that the inside limits of integration are going to have a variable in one or the other of them. Okay, so our variable in this one has a 2 over x as the upper limit of integration. Okay, so the process isn't any different. It just means that it's going to be, the numbers are not necessary. It's not going to be evaluated at numbers. That's the only difference in what we're really doing. This also just is a different kind of function. We have the function e to the xy. So let's take a look first and do that integral. So what is the integration or the antiderivative of e to the xy? Yeah. So e to the xy, right? And then we need, basically we're doing u substitution, if you will, right? The exponent xy is the variable y times the constant x. So we get a fraction of 1 over x, or you could put x underneath the e to the xy part of that. Okay? This is the first one where we've actually had x times y in something as well, not just an exponential, but... All right, and we need to evaluate this at 2 over x and at 0. So, plugging in the 2 over x, I have for what variable? Y. E is not a variable, right? And x isn't the variable we're working with. You were already pushing through with it. Gotcha. Okay. So we're going to have the 1 over x. And then we're going to have, if we plug in 2 over x for y, what do we get for the first one? E squared. Right. And then we're going to subtract, and we're going to evaluate at the value 0, which is going to give us what? 1 over x times 1. Right? So we still get a 1 over x here. And I think I erased something wrong. Oh, I just didn't write that as a 2. Okay. So now we're going to integrate from 1 to 2 dx. If you want to factor the 1 over x out and think of it as a factored value, you could do that, or you can do them in 2 pieces separately. Either one works fine. I'm going to leave mine separate because I already wrote them. But all right, so what is the integral of 1 over x times e squared? Right, okay, so there's going to be this e squared, it's a number, and then we've got the natural log of x. And I'm not going to bother with the absolute values because my limits of integration are already positives, 1 and 2, so I don't need to worry with that. And then I'm going to subtract, and what's the antiderivative of 1 over x? Natural log of x. And we're going to evaluate all of this at 2 and then at 1. Okay, so tell me what I get when I plug in 2. You get what? Say it again for me. Natural log of 2 times e squared, right. Or in the other order. Oh, that's a weird looking e, isn't it? Let's try that again. So e squared natural log of 2, or natural log of 2e squared, and then minus natural log of 2. Okay, now what happens when I plug in the number 1? You get e squared natural log of 1. What's the natural log of 1? It's 0. Yeah. So this actually gives me 0 when I plug in the number 1 into natural logs. So my answer is actually e squared natural log of 2 minus the natural log of 2. Or you might see it written perhaps like in the back of the book, something like natural log of 2 times e squared minus 1. They might factor it out. Yeah, I don't care whether it's factored out. It doesn't make any difference. Either of those are perfectly fine. You just did your first double integral over a random region, right? Okay. We're going to do one more, kind of like that anyway. And then we have one more variation after that. All right, so we're going to find an integral equal to the volume of the solid bounded by the given surfaces and evaluate the integral. Okay, so the last problem, we didn't have these sort of descriptive phrases because we actually already had the problem set up for us, right? They put the numbers 0 or 1 and 2 in, they put the 0 and the 2 over x in. This time we're going to start a step back from that, and we're going to actually start with the equations given to us and all the bounds given to us, and we have to create the definite integral that we're looking for. So our function is z equals 6 minus x minus y, and then our bounds are z equals 0 x equals 4 minus y squared, and x equals 0. And we have to create the double integral we're looking for. That's the difference right now. We got to create it. All right, so first of all, notice that this z equals 0 is just going to be a lower bound. That's the xy plane. So we're actually saying trap between that xy plane and whatever the surface is on top. So that's what's trapping it. So that z equals 0 is not going to come into my picture of what I'm going to draw. It's just talking about the xy plane itself. But what I do need to do is I need to draw the xy plane much like we drew the xy plane beginning when we did the rectangular region and split things up, and figure out what this region actually looks like. Okay, so we're going to draw an xy plane. And I know what x equals 0 looks like. That's just the y-axis, right? What is the equation x equals 4 minus y squared look like? It's a parabola. How? Like, what does it look like? Opening to the left. Okay, so it's in either a left or a right parabola. How do we know it's left or right instead of up or down?
It's y squared.
Because it's y squared, exactly. If it were x squared, we'd be looking at something opening up or down. Why does it open left?
Negative.
Because there's a negative y squared, exactly. And so it opens left, so it's going to open like this. What's its vertex going to be? Say it, Taylor.
4.
4 on the x-axis. Good job. All right, so we're going to go over here to 4 on the x-axis. And we're going to draw the vertex, and we're going to open the parabola opening leftward. What are its x-intercepts? I'm sorry, its y-intercepts going to be? Where's it going to cross the y-axis? 2. And negative 2. Fantastic. All right, so my parabola is going to look like this. And it's got to be trapped between that parabola and the y-axis, because I already drew that y-axis and is one of my boundaries. So I end up with this space inside.
I missed it. What is z equals 0? Why? What's that?
The z equals 0 is telling us that we're going to be above the, well, in this case, because it used the phrase above, right? Bounded by the surfaces. We're going to be above that shape. That's the lower bound.
Okay, gotcha.
Okay? Yeah, that's going to be our cutting off spot, if you will. So we've got this sort of parabolic, or portion of a parabolic curve, you know, on the xy plane. We've got some surface happening around up here in 3 dimensions above it, and we're finding the volume that projects, you know, down basically onto that 2-dimensional parabolic shape. Okay. Here's where we have a little bit of choice. This is very nicely already set up, telling us that x goes from 0 to 4 minus y squared. Agreed? We already have sort of the equations, if you will, about our boundaries solved for x. Because we already have them solved for x, it's very natural for us to use those values. 4 minus. To use those values as the inside integral. So we don't have to. We could solve this for y if we really wanted to, and we could switch these all around, and we're about to do something very much like that in a moment. But this is already set up solved for x. So we might as well use what we already are given. So here's my function inside here. And I'm going to do this with respect to dx, because those are limits of integration on x. Now I've got to figure out, based on my diagram, what are my upper and lower limits on y? Yeah, negative 2 to 2. This feels a little bit like doing regular integrals when you did things like surfaces of revolution and solids of revolution, and you had to look at a rectangular region and figure out where did it start and where did it stop. It feels a little bit like doing that. So this one goes from negative 2 up to 2. Now, there's some pretty cool stuff with symmetry you can do on this particular one in a moment here. I'm going to avoid doing it because I just want you to see in general how this would work if you didn't have symmetry involved. But there is some cool stuff with symmetry if you happen to notice it, because this is over a symmetric shape in the xy plane. But let's take a look at what we've got first. Inside of that red rectangle, we need to evaluate, or sorry, we need to do an antiderivative for 6 minus x minus y with the variable x as my variable. So, what's my antiderivative? 6x, right? X squared over 2, or 1/2 x squared, minus yx, or xy. And we're going to evaluate this at 4 minus y squared and at 0. So I don't know about you, but evaluating at 0 is very friendly. Yeah? Evaluating at 4 minus y squared, not so friendly. Okay, so let's actually do the evaluation then. So we've got 6 times 4 minus y squared minus 1/2 times 4 minus y squared squared minus y times 4 minus y squared. And we already said this is then minus 0, so I'll write it in there just as a reminder that we did, in fact, check that. All right, so do a little bit of algebra for me. You guys are fantastic at algebra by this point, aren't you? Like, it doesn't even faze you the slightest to do algebra at this point. All right, so go ahead and FOIL things out, combine like terms. I'd like to know what we have that we're going to actually integrate as a combined, completed, consolidated, as much as we can anyway, value on the inside of this integral. All right, so let's do this in decreasing order of exponents, not because there's anything special about that, but that way we're all saying the same thing. So what is the first and highest exponent term you have? Negative 1/2 y to the 4th. And then what? Y cubed, good. What else? Oh my goodness, hang on just a second. All right, minus 2y squared, is that what I heard, Nathan? Okay, then what? Minus 4y. And finally? Plus 16. Excellent, that's what I have as well. All right, so let's do an antiderivative now of that function. Somebody tell me the first term. Negative 1/10 y to the 5th. Good. Somebody else tell me the second term. Good. 1/4 y to the 4th. A no person. How about tell me the third one? Fantastic. Someone else. Negative 2y squared. Okay, and someone who hasn't given me an answer yet recently, tell me the last one.
Plus 16.
Thank you, Brandon. 16y. All right. And we're going to evaluate this at negative 2, well, at 2 and then at negative 2. So I'd like for one of you to evaluate it at 2 and one of you to evaluate it at negative 2. Have a volunteer? Who wants to volunteer to evaluate it at 2? Caleb, and you want to do negative 2 for me, Nathan? Fantastic. Let's go with fractions, because I don't think this one has an ending decimal that's nice and clean for you. Okay. And then into fractions for me, Caleb.
292 over 15.
Okay, so we have 292 plus 412 over 15 for a grand total of what?
704 over 15.
Perfect. 704 over 15. Very nice. Okay, so now this one was very natural for us to choose to do x as my inside because I was given the values. It was equally easy to do the integral for this. There's no reason to have done it in a different order. Sometimes, however, it is nice to switch the orders of the integration. So the last example I'm going to do is I'm going to show you how you look at things to switch an order of an integration. And again, this is going to feel somewhat like when you were doing limits of integration on integrals with solids of revolution in Calc 2. Okay? So we're going to do an example where we're going to change the order of integration. Now, if we just had a rectangular region, all we'd have to do is just switch them. I mean, there's nothing really to do. They're all just numbers. The problem is we don't always have numbers in our integrations, right, our limits. So we're going to take this one is our integral from 0 to 1, integral from 0 to 2y, and we're going to actually have a function. We're just using f of xy because we're not integrating, we're just changing the limits, dx dy. So what we want in our answer when we're all said and done is we want this to say in two integrals. It's going to have f of xy, and instead of having dx dy, it's going to have dy dx. This is our goal. We just have to figure out what numbers and variables or function values go at each of those places in order to allow us to switch them. Okay. So what we are going to do is we're going to look at what we're actually given. This information tells us what? Right. So this tells us that y is going to go between 0 and 1. What about this one? Right. X is between 0 and 2y. So what we're going to do is we're going to go back to a two-dimensional picture and we're going to graph what we have there, sort of written out in inequality form. So I need my y value to go from 0 to 1. So I am above the y-axis. I need my x value to go from 0 to 2y. Okay? All right, so I need to draw the equation right here that this is describing. That is the equation that is x equals 2y. Right? So x equals 2y is equivalent to having y equals what? 1/2 x, or x over 2. So I've got a graph of a line which has a slope of 1/2. So I'm going to go over up 1 over 2. Let me get it in there right. So this is the equation that I've got for this line. Something like that. I've got a couple other lines I'm supposed to draw. I'm supposed to go from x equals 0. Well, x equals 0 is also known as the y-axis. So I'm going from my y-axis over to that black, diagonal line that we just drew. Okay, so I'm between those two things, which means I'm in this area right here. I mean, that's what that really means. Or potentially in the area down here. I just have to figure out which one it is. Well, which one it is based on the fact of what y is. Y is going from what to what? 0, which is also known as the x-axis, up to the y value of 1, which would be right here. So what am I going to shade in as my region here? Yeah, it's a little triangle right in here, isn't it? That triangle is my region. So I want to take that triangle, which I know all the values for now. This is y equals 1/2 x. And I want my y values to be determined. So what is the minimum y value and the maximum y value of this function? It was 0 and 1 at the very end. What would if we used the equation of the line, though? Let me back up and let me ask the question a different way. Let's talk about x. What are the limits of integration on x, numerical value limits of the integration on x? 0 and what? 2? I think so. So 0 and 2 are going to go on the outside. So my x value is going to start at 0, my x value of 0, and it's going to go out to an x value of 2. Now think about y. Take any, well, this is how we did it in Calc 2, a representative rectangle. Remember that? And you looked at taking that representative rectangle, which you could barely see because my purple's so dark underneath. And what's the lower value for y? Where does y start in that rectangle? It starts at x over 2, right? It starts at that horizontal, or not horizontal, but that diagonal line. This minimum right here for my y value is actually the line that's x over 2. So down here in my limits of integration, here I have x over 2 as my lower limit of integration. What is my upper limit of integration then? 1, and it's constant, it never changes. So this is what my evaluation actually changes into when I change the limits around. And do you see how important that picture is in order to make that happen? You're not going to be able to do this without that picture, I don't think, okay? There may be a very good reason why you don't want to integrate that with respect to one variable to the other. Think about some of the things that were unintegrable without like tables. You had to use table values for it or something like that. There are cases where the integration works much better in one variable and ignoring the other one and then switch it around afterwards. So that's the reason for recognizing that it's possible to do. All right. Homework. This is a very long section, both what we did in class today and in the homework, so brace yourself for that. Normally I would tell you you might want to just not do any of the homework until after the test. I think probably doing this homework assignment between Tuesday and Thursday next week might be a little overwhelming, so I'd probably spend the next couple of days working on this assignment, then put it away, and then focus on the test because this is kind of long. So we're looking at 2, 3, 5, 8, 12, 15, 18, 22, 25, 28, 31, 38, and 42.